So I guess I want to bring your attention to these formulas that I wrote down at the beginning, because what we are going to do now is going to look familiar with what we did with the electricity. So I have a list of common geometries for generating magnetic field. So you've seen two geometries. The geometry for this, the coils, and the geometry with a hypothetical infinitely long wire. And we applied the Biot-Savart's law to get this formula. There's two more geometries that you can see, actually three more geometries. One of them is highly impractical, so we never use it. The other two geometries are actually highly practical, and we do use it all the time for generating magnetic field. So this is one such a geometry. So at some point in the semester, you'll be building these. Let me just pass two of these around so that you have some sense of what we are talking about. And why are all these complicated? This is for the transformer lab. Okay, these two. So this is one. And for this, the second one that I'm passing around, you have to imagine that it's all wrapped around so that it looks kind of symmetric. So these are the example geometries for generating magnetic fields. So geometry for producing magnetic field. The thing that's getting passed around right now is the geometry called the toroid. And it looks like a donut, but the important part of that donut is when you have this sort of donut-looking underlying geometry, then we have to describe how the current is going around in the geometry. And the current that's going around here, it wraps around the outside thing. It wraps around here. It goes here, comes down here, goes back here, comes up. So you have to imagine this loop sort of going around the whole thing. Okay, I'm getting tired of drawing this. You have to imagine this loop going around and ending back here. So everyone saw the toroid? So have a mental image of what this looks like. So this toroid is one practical geometry. The second practical geometry is what we call solenoid. It's like the coil of wire, except you space it out uniformly and you make it over a length. And this is one setup that can produce magnetic field. Let me just demonstrate with this quick demo. This is a steel ball, and this is actually a steel bar. But you can see that steel doesn't actually attract the steel. It has to be a magnet. So let me turn this steel into a magnet. I can put this steel bar inside this coil of wires, and it's still not a magnet. But once I pass current through this coil of wires, all right, turn it on. Oh, it was already on. Turn on the current. Okay, then it becomes a magnet. And when I turn the current off, it's no longer a magnet. So this is actually, when you think of electromagnet, the kind of electromagnet that they use at, I don't know, metal recycling center, then this is the electromagnet that they have. So, so this particular arrangement is an arrangement called solenoid. So what a solenoid would look like is, imagine a cylinder, and I guess we do imagine a cylinder of a circular base for a reason that we'll go over later. And the way we have to imagine the wires sort of wrapping around in a way that it almost looks like a coil of wire, like what a spring would look like, that it wraps around. And this solenoid geometry will also produce magnetic field. In a way, it's practical, useful. And I just want you to imagine applying Biot-Savart's law to either of these two geometries to figure out the magnetic field. For example, magnetic field over this cross section here. Like, imagine coming up with some expression for the integral and actually integrating over all these different wire segments. Or for the solenoid, I guess for the solenoid, it's actually easier to imagine. If you stick to the positions along the axis, then you can just use the superposition principle. We have a formula for the loop. Imagine loops is being spaced out in such a way. Then I think you can actually do it. But imagine trying to find the magnetic field region outside here. Like, what is the magnetic field here? And one of the surprising results that we are going to find out with the solenoid soon, probably on Wednesday, is that the magnetic field just outside the solenoid is going to be 0. And if you imagine trying to use Biot-Savart's law to derive this, it's going to be mathematically complicated. And you saw an aspect of this with electrostatics. So we started out with the Coulomb's law. I derived the electric field for a line. And then I said, it's going to take too much class time to actually do this. In class, I made videos for a plane of charge and a sphere of charge, and line again, just so that it's all there. And you saw how mathematically complicated it was for a sphere of charge. You needed all the tools from a multivariable calculus that some of you probably haven't taken yet, or it's not required for this class. Magnetism, even the basic law is more complicated than electricity. So when you try to apply to this directly, it's so complicated that I'm not even going to try. I'm not sure if I know how. So that's the situation where we are. If you try to use Biot-Savart's law to calculate magnetic field directly here, you won't be able to. It's just mathematically too complicated. Now, there are two toy situations where you can actually use Biot-Savart's law to calculate magnetic field. You have seen one of those toy situations. So I guess let me just label these. These are useful geometries, as in you will see these in actual experimental setup where you need to generate magnetic fields for some reason. And here are some toy examples. So toy example geometries is, well, one of them you have seen before. One you have seen is the line. So just a long line of current. So if you have a current that's flowing in a long line, then that would generate magnetic field, right? It would generate magnetic field sort of going around this way. And I call this toy example because, if you wanted to actually generate magnetic field for use somewhere, you do not do that with a single wire. Because you've seen in our previous calculation, the amount of magnetic field that's generated by a single wire carrying on 1 ampere of current, just so tiny that you wouldn't be able to do anything useful with it. So that's one. The other toy example that I'll mention, because this is the last of the 4 geometries that exhibits a particular kind of symmetry that allows you to calculate magnetic field in a different way. The last of the toy example is a plane of current. Can people here even imagine what a plane of current looks like? Kinda, maybe. 2 different ways you can imagine it. You can imagine this current carrying wire, and you just have them all spaced out over a plane. Then that would be a plane of current. Or you can imagine, this is how I like to imagine it. I imagine, let's say I have these charges arranged over a length of a line, and imagine it sweeping across. this charge sweeping across would represent a plane of current. Obviously, this is not something you see in like a practical object. This is a purely theoretical abstract object that you can use to do calculation, and you can have this plane of current to do calculation. So the way I like to imagine is as a side view. So imagine you are looking at the side of the plane. So this is the side of plane, and you can imagine currents, I don't know, going into the board. So this would be the multiple wire imagining. So you've seen us calculate magnetic field for a line using Biot-Savart's law, right? And can you imagine doing it for a plane of current also? Yes, no? Yeah, I mean, it's once again, it's going to be mathematically complicated, but you can imagine. You can imagine, calculate the magnetic field due to 1, and that's a small segment of the plane, and use the superposition principle. Imagine adding up all those segments over, so you integrate over the entire plane. That's another 1D integral, and you can imagine calculating magnetic fields that way. I'm pretty sure your textbook does it, so you can look at it. We won't actually do that in class. It'll take too much time unnecessarily. But what I'm trying to illustrate here is, this calculation was not an easy calculation. And this calculation, when you imagine doing it, it will be still harder example. It will involve integrals that I have to look up on Wolfram alpha. So how did we approach these problems with electricity? So when we, so the calculational examples where we said, okay, even though in theory we can use Coulomb's law to work out these problems, this is way too difficult just mathematically. Do it using Coulomb's law. What did we do? So we used the symmetry, and the way we used the symmetry was we used it with the Gauss's law. So that's what I want to, oops, wrong color. That's what I want to start thinking about as we cover Amperes law. So because all the intuition you built up with the Gauss's law is going to apply to Amperes law. So let me just remind you of Gauss's law. What Gauss's law said was this. So you calculate electric flux. You calculate electric field, dot product with some area element, and you add it all up for some closed surface. So you integrate over some closed surface. And what Gauss's law told you is that this quantity is equal to amount of charge enclosed times some constant, right? Let me ask you a couple of questions that I hope you remember the answers to. Is this law always true? As in, let's say you have this highly asymmetric situation where you have a dipole, let's say a positive charge and negative charge, and you try to apply this Gauss's law to a surface enclosing the negative charge. Can you still rely on this Gauss's law? Is Gauss's law still true? It is still true. Yeah, it is a fundamental law of nature. If you ever find a situation where this is untrue, you have, well, that's just not going to happen. It's like, yeah, it's just not going to happen. Science itself is wrong if that happened. So given that it's always true, what was the whole thing about the emphasis on symmetry? Like whether it's symmetric or not, this is still true. So why do we care about symmetry? To make the integral easier. So here the challenge is actually in the application, because this calculates the electric flux, but we don't care about electric flux. We don't care about electric flux. What we cared about was always the electric field. And when you look at Gauss's law, even though it's true, electric field is always inside the integral. You have to find the situations where you can make the integral easy enough that you can actually pull this out of the integral without knowing the exact form of electric field. Then you could proceed to solve for the E and actually get the answer for electric field. That's the same thing we are going to do for magnetism, except it's not going to be Gauss's law because this was the fundamental law for electric field. For magnetism, we are going to use something called Amperes Law. So the relationship between Amperes Law and Biot-Savart's law, it's the same relationship, or it's the analogous relationship between Gauss's law and Coulomb's law. They both express the same thing. But Gauss's law was easier for calculating electric field when you have a highly symmetric charge distribution. It's going to be the same thing for Ampere's law. It expresses the exact same thing as Biot-Savart's law. It's equivalent to Biot-Savart's law, even though we are not going to prove that. But it will make it easier to calculate magnetic field for these situations.